Hello everyone, welcome to another emerging tech bite session on Let's Learn 5G from the scratch for our beginners. This is a series on 5G where we are covering all the 5G underlying technologies from the scratch for our beginners. So this is the diagram that we had shown in our previous sessions as well. There are already two sessions has been done and uploaded on this channel. This is our third session. So if you have not seen those sessions, I would highly encourage that you please watch those first because we will be building on top of that. So in the previous two sessions, what we have talked about is about the UE, and then we have also discussed on the radio access network part, some of the key capabilities under that. In this session as well, we will be looking at this side of the picture, and in particular, we'll cover one technology which is called as MIMO. MIMO stands for multiple in, multiple out, and in the context of 5G, this is known as massive MIMO as well. So I will keep this discussion at a very basic level, will not go in much of the details around 5G, but massive MIMO, but we'll cover some of the high levels so that you can connect the dots what MIMO is. So that is our first topic on the agenda as well. What is MIMO? And then we will look at what does this massive keyword means with MIMO. We will be looking at some of the historical perspective because it is necessary to understand why this technology was brought in the first place, what challenge it was solving back then, and then how it had evolved into what it is today. Is there any effect of the frequency on the antenna size? Because 5G, as we had seen in the previous lectures, use a wide band of frequency. So when that goes to the antenna, on the size, is there any impact of that? We will look at that. Then we will come to 5G massive MIMO. We'll cover another adjacent concept, which is beamforming. And then we will end our lecture towards like with the UE, how a UE select the best beam that is available to it. So with that, let's start our third lecture in this series. So to increase the performance of this 5G new radio, we had already visited some of the key technologies like OFDM, the MM wave spectrums, dual connectivity, small cells. We have covered all those aspects in the previous lectures. In this, we will be looking at these two. So to start with, what exactly MIMO is, it's a multiple in, multiple out. It's a radio antenna technology which deploy multiple antennas. So you have this TX side, and then you have on the RX side, let's say this is your antenna. So you deploy multiple of them on both the side to increase the throughput, reliability, quality of the link parameters basically. So we'll see those. How does this work? Currently, we are just covering the definitions. So let's go a bit deeper and cover MIMO from the historical standpoint. And when we go for MIMO, this is used in wireless communication for a very long time. In fact, MIMO was initially introduced in release 8 of 3G by 3GPP, which is a standard body. And back then, it was used to solve some key challenges. And to understand those, we need to understand what spatial diversity is. And the second concept is spatial multiplexing. So let's understand these two terms. By an example, and then we'll come to the MIMO. So this is a very simple topology where we have our tower, which is sending the signal in this direction. And let's say we have our receiver here, which is a UE. So when the radio signal travel certain distance, it tend to deteriorate, which in turn means that some of the information may get lost during transmission. So how can we avoid this, or how can we minimize this information loss? So over a period of time, there were multiple technologies which introduced to address this. The first one was time division multiplexing. What time division multiplexing says is you transmit the same signal over multiple radio paths at different time slot. So the receiver gets the same information over different time slots. So that way, the chances of getting the information lost are minimized. There is another technology which was introduced is frequency division multiplexing. What frequency division multiplexing says is you transmit the same information over different frequency channels. So that way, the UE can reconstruct the information, whatever it is receiving, and there are chances of information getting lost are minimized. Along with it, there was another technology which was called as space division multiplexing. What you mean by space division multiplexing is that you put multiple antennas. So this is your antenna 1, this is your antenna 2 on the transmitter side, and this is on the receiver side. And then you send the information over different radio paths via these two antennas. So you are sending the information 10101. If this information is sent only over this path, there are chances that some of the information that you see here may get lost. But if the same information is sent here as well as here as well, there are high chances that the same information will be received. And this putting up these multiple antennas is called as MIMO. Now let's take a look at two aspects. One of them is diversity, another one is multiplexing. So thought behind this diversity is to provide the same signal to the endpoint receiver, and the same information is transmitted. So that way, the spatial diversity takes the advantage of these multiple antennas to transmit the same signal via different radio path. So that way, we are improving the reliability of the link. So your diversity directly translates into reliability of the link. But very soon, this spatial diversity had translated itself into another complex concept, which is called as multiplexing. So let me get rid of these ink here on the slide. So what the multiplexing means is that you send the information. Let's say there is a virtual pipe here in between, and I have this information to send. what I will do is I will send 101 here. There is another virtual pipe because we have another radio path available over here. This link, let's say, is of 75 MB. This link is also of 75 MB. That way, I'm getting a cumulated throughput of 150 MB. And I can send the information faster. So multiplexing results in more throughput. Diversity, as you recall, was meant for reliability. So putting the concept here, whether you are using it for diversity or multiplexing to increase the throughput or reliability, but you have two antennas. And the concept of putting two antennas or more than two translate into MIMO. So this is multiple in, multiple out. And these days, it is very common for both the mobile devices and the network to have multiple antennas to enhance the connectivity, to provide better throughput and better quality. So I hope this is clear now. Let's move on to the effect of antenna size when we have this wide range of frequencies. So how does the antenna size vary with the wavelength? So wavelength, we all know that it is denoted by this lambda. And in 5G, we have the low band, mid band, and high band, which translate to your wave as well. And when we go on this path, this we call it millimeter wave. So what it means is that this lambda value is getting reduced. So your wavelength is reduced. It's like in the millimeter when you go to waves. So what does this have the effect on the size of the antenna? So for example, here I'm showing you a 3 gigahertz antenna panel, which by looking at the picture itself look much bigger. And then here we have 30 gigahertz where you see these small antennas. So what it means is as your frequency increases or when you move towards the millimeter wave, the size of antenna get reduced. And there is actually a formula to calculate this. So the wavelength lambda can be calculated by C by F. C is your speed of light. F is the frequency. So I have some populated data. For example, if you have 700 megahertz of the frequency band, antenna size will be 42.85 centimeter. And this actually comes via this formula. For 3.5 gigahertz, it translates to 8.6 centimeter. Or if you go towards the millimeter wave, 28 gigahertz, it come down to just 1 centimeter. So you see here the antenna size is getting reduced. So when this antenna size is getting reduced, what we can do is on the panel, we can have these more and more number of antennas. And this is actually called as massive MIMO. So massive MIMO is simply an extension of MIMO which extend these legacy system by adding much higher number of antennas to this base station. So you can see like 16 units of antenna, 32 units of antenna, or maybe even higher than that. Uh, Normally, what we say is if it is 16 or more, that can be called as massive MIMO. But now going back to my previous slide where we were using spatial multiplexing, if we combine all these antennas for the TX, how much throughput we can gain. But when we like take advantage of these multiple antennas, we also need to look at the UE side. So on the UE, whatever UEs are available as of today, they have four receive antennas. So that means I can like use 4T and 4R for a particular endpoint. These ways I can combine my four antennas. So if let's say one antenna is providing a speed of somewhere around 75 MB, so it can come to a 300 Mbps, which is a decent number in terms of bandwidth, and which 5G is also targeting. Uh, So with 300 Mbps, we can have this. Now, what is the other advantage of this? The other advantage, like, okay, with this UE, we are getting 300 Mbps. Then let's say there is another UE that can be served by another group of antennas, and you get the same 300 here. Then you get the same 300 here for another UE. So this way, you see your throughput is massively increased per base station. So that is what we call as massive MIMO. So I hope this is clear. There is another adjacent concept to this where what will happen if we combine like these many antennas. So what exactly it results into is a beam. So there is a beam forming that happens when you combine more number of antenna elements which are present in the tower. So when there is a beam which is formed, is there any impact of it? So this is again just the definition. So massive MIMO technology use large number of antennas that we had seen, 32, 64 or more elements, and more number of antennas uh, result in the better services to the UEs, and number of antennas in the array are larger than the UEs. Now we will look at what this beam is. So when we combine these multiple antennas, is there a change in the signal that is getting transmitted by the transmitter? So let's try to understand the concept of beam forming. So let's say we have this one antenna, which is here. So when it transmits the signal, it goes like this. It's like you turn on the light and then it scatters in front of you in all the places. But then what was seen is if we combine more than one antenna here and fed them with the same signal, it actually results in a bit more focused beam. And as we know that the MM wave, which is a high frequency wave, it actually take this further and enable a directional communication with large number of antennas. So when we put more than two antennas, what it results in a much more focused beam. So when this your beam is very much focused, it actually need a very precise alignment with the G node B and the UE. But we will look at this beam management at the later part of this lecture. How does the UE know which beam it need to select? But for now, you need to remember this, that when there are more antennas combined, the beam that is formed by these is a sharper or much more focused beam. Now let's look at the beam management in 5G. So 5G is actually a very wide band of spectrum where we have sub 6 gigahertz of beam and millimeter wave of the beam. In case of millimeter wave or sub 6 gigahertz band, there is a difference. Like we are going from mid band to the high band. So things related to propagation, signal, fading effect, all those comes when you go with wave because they cannot cross an obstacle, they cannot cross a larger distance. So when the NR, the new radio manage this wide band of spectrum, it actually introduces some new challenges for the system design. And it also affect the end-to-end throughput and the experience. And as a part of 5G, throughput is one thing that we were targeting the most. So to overcome these limitations, 3GPP has defined new physical layers and MAC layer, which is your layer 2 mechanisms to support this directional communication. And one aspect of it is the beam management. Before we get into the concept of beam management, from the UE perspective, let's understand 2 points. One is your UE can be in the idle mode or it can be in the connected mode. So when it is in idle mode, that means it does not have any active transmission. It is the device is just turned on, or it is just like waking up, and then it's looking for some signals to synchronize. In the connected mode is where there is some data exchange which is going on. So this data exchange is taking place, and that's where we need some more precision because UE and G node B, when this beam is focused or a directional beam, and if the UE is moving within that cell, it become actually challenge to manage that in the real time. We need to have that healthy link all the time. So this is what we will be discussing, like how does the UE select the beam, because this highly directional beam forming architecture, for these antenna elements is very crucial for 5G because 5G is for enhanced bandwidth. If we are using multiple antennas, that way we can serve the UE with much more enhanced bandwidth. So there are some special procedures that we need to look at when we are managing this. So this can be categorized into these three pieces: the beam sweeping, the measurement and determination, and finally the beam reporting. So beam sweeping is It's used during the initial access by the UE to choose the best beam. So what happens is your G node B is transmitting the beam in all the direction at a UE towards the UE in a different time interval. So whenever a UE is synchronizing with the network, it gets those beam and it actually read some information out of that beam. So those are like the primary synchronization signal, which we call a PSS, then secondary synchronization signal, and then it also receives some physical broadcast channel, we call it as PBCH, or demodulation reference signal, which we call it DMRS. You don't need to go in the depth of it as of now. Just think that the G node B is transmitting, and these are the parameters which are basically looked by the UE, or this is the threshold which is set by G node B, that the UE need to select the best beam which is applicable for it. So when the G node B actually transmit these beams, we have something called as synchronization signal block. So what the synchronization signal block is, let's say this is, let me get rid of this ink here. So this G node B, it transmits the beam in this direction, then in this direction, in this direction, and then let's say in this direction. So you see there are like four beams. So this one block of this is called as SS block. We call it synchronization signal block. And all of these blocks, let this is one, let's say this is two, this is three, this is four. All of these are called as SS burst. So this SS burst is repeated periodically with a time frame of around 20 milliseconds. And then the UE, which is here, just scan all these SS blocks and select the best one for its use to transmit or receive the data. And that actually depends on number of the parameters that we have looked some time back before. So now how these SS blocks are decided. So actually this depends on the frequency. So we have visited these bands like in 5G, we have this FR1 band, and up to 3 gigahertz, we will have four blocks, like as I have drawn four, right? So four such blocks will be there for FR1 up to 3 gigahertz. In the same band, if we go up to like from 3 to 7.125 gigahertz, these blocks are 8. And if we go to FR2, which is your wave segment, these blocks can be up to 64. So you see, as of now, I have drawn like four blocks in this. If we go with 64, how directional it will be, like the beam will be very small. and it will be like very near to each other so that it can cover like much more directional beam due to limitation of space and the pen I'm not drawing. But think of it like the beams which are very close to each other. So earlier, let's say if we look at an angle of let's say a 60 degree, so in the 60 degree here we have two, but if we go with wave within that 60 degree within the same space, you will have much more directional beams. And G node B just transmit all these over a regular period, that too repeatedly. So whenever the UE synchronize, be it in ideal mode or connected mode, depending on where the UE is. If it is in ideal mode, it will synchronize. So UE measures the beam strength by the received signal. And in ideal mode, this actually depend like it is a synchronization signal, so it measures that strength. But if it is connected mode, it is based on the CSI, the channel state information for the uplink and downlink. So UE searches the best beam periodically using some predefined thresholds. Those are set by the G node P. Why periodically? Because if you are connected and you are moving in between that cell, there are high chances that you are running maybe out of one beam and then like getting near or closer to the other beam, or that beam need to adjust itself. So there are concepts where that beam will move along with you, and as far as you are in the reach of the same tower, so it basically move towards you. So this actually happens in this beam measurement and determination section. The third is the beam reporting, where actually the best beam identified by the UE is reported back to the G node B. And this it tells via the CSI feedback. So this is how we have covered it at a very high level, but this is how your UE select the best beam which is available to it. So what we have seen in this lecture today is that the benefits of massive MIMO, it results in increasing capacity, improved coverage, and which results into a good user experience. So with that, we would like to end this lecture today. If you think this is something good, give us a thumbs up. And I would like to connect you over the LinkedIn. So the link is here and it is mentioned in the description box as well. Uh, I hope this was informative and happy learning. Thank you very much for your time.